So welcome to the simple linear regression chapter. I'm Dr. Tay over here, and I will be taking over the last section, of your EEE 382 course on probability and statistics. So simple linear regression deal more on the statistics side rather than the probability. Okay, let's proceed. So what is the meaning of regression over here? Regression means that we want to predict a certain thing. Okay, we want to predict. Regression also means to predict. And based on our foundation knowledge, we know that we can simply predict anything, okay, based on a simple linear line. So the equation of a simple linear line, we also know that the equation is y equals mx plus c. And in this case, instead of using mx plus c, we say y equals to beta x plus alpha instead. And of course, alpha and beta can range from 1 to n or any other values, okay? And if we plot out this straight line, and this is a generic y equals to mx plus c line, okay? Instead of m and x, instead of m and c, now we use beta and alpha. It's just a matter of notation. And the problem is that we want to find this straight line so that we can predict what is the output value y based on an input value x. But the problem is we do not know what is the value of the alpha and beta. Okay, but common sense tells us that if we can know what is the value of a certain value x input, then we can predict or regress the output value y based on the regression line that we have predicted. Makes sense? So, and the regression line, since we say that the regression line at best is only a prediction, the outcome of the prediction definitely comes together with a particular value of error. And we need to capture this error in our equation as well. And this is why the y equals to beta x plus alpha initially that we introduced in the previous slide now has an added terms of a Greek letter E over here. A Greek letter E here is what we use to represent the error in our prediction. Okay, so pay attention to the notation over here, beta, alpha, and E over here, because later on we want to differentiate it with our predicted regression line, okay, and the true regression line. A little bit of concept before we proceed to the derivations of the equation is as such, okay. Just imagine that this is the regression line that we have actually predicted. Okay, let's say that this is a regression line that we have predicted, and this is each of these vertical line, dotted vertical line over here, okay, represents a particular input value x. Okay, and then we want to use this input value x to predict the output y based on the regression line that we have constructed. So if we start from this, let's call this x1, yeah? Based on x1, the true regression line, okay, before that, yeah? Let's also say that this black dot, okay? This black dot represent the true response value of each of the respective x value. So based on x1 value and based on this regression line, yes, so happen that we obtain that output value y, which is the black dot, that is also predicted by the regression line over here. But in x2 over here, the true response is this black dot, but the regression line predicted that the response is over here. When we are at x3, the true response is a black dot here, but the regression line predicted that the value is over here. When x4, when you're given x4, the true predicted y value is this, but the regression line gives us over here. So if you can notice, right, the difference or the distance between the black dot and the intercept between the x vertical line and also the and the regression line represents an error in our prediction. And generally, if we take enough of this data and we observe enough trend, we see that this error is actually normally distributed as